This is the Turf Zone Podcast, your central information and news hub, bringing together professionals from turf associations across multiple states to share things to help you in your business. Brought to you in partnership with our friends at the Alabama Turfgrass Association. Now, let's get in the zone.
Welcome to the Turf Zone. In this episode, we feature an article titled Looking to the Future, Where Will the Turfgrass Industry Be in 10 Years? Equipment and Technology of the Future, Part 2. The next step in the evolution of turfgrass equipment and technology is upon us. University and corporate researchers agree that over the next 10 years, the advancements will be nothing short of amazing. This is due to the perfect storm of several factors. Technology has progressed to the point where it's being applied to all aspects of equipment design. Materials are in short supply, and even if the item is available, a high cost will require managers to conserve and eliminate waste. Environmental awareness, including the intelligent use of pesticides, fertilizers, and water, are important to the turfgrass industry because it speaks of our professionalism. Most importantly, the growing labor shortage we've seen is not going away anytime soon. All these factors have been noticed and are being addressed by those developing the next generation of turfgrass equipment and technology. It's impossible to fully prognosticate the future with complete accuracy. However, to confirm the incredible direction that equipment and technology design is heading, here are a few hypothetical scenarios that have real promise. Sometime in the near future, a golf course superintendent launches a drone for a routine fairway flyover to look for signs of insect infestations, especially armyworms, since historical data alerts the superintendent that armyworm infestation may be possible this month. The drone is equipped with a sensor measuring vegetation indices, which can detect turfgrass health and stress by measuring leaf tissue biomass. A reduction in turfgrass biomass indicates where armyworms might be feeding. The drone's onboard high-resolution RGB camera is also used to photograph any location showing a predetermined level of biomass reduction, while GPS technology captures the coordinates of those locations. After photos are reviewed, armyworms are discovered and confirmed by ground truthing. Mapping is created using GIS technology to identify locations showing less biomass and increased stress than 2 days before, while compensating for mowing. Since the caterpillars were discovered before much damage is done, the infestation is localized. The decision is made to send a second drone for site-specific treatment. This spray drone is given the GPS coordinates mapped by the first drone to precisely fly along a pre-programmed route and spray only the turfgrass needing treatment. On subsequent days, additional drone flights are made to monitor the treated locations for biomass increase, regrowth, as well as other possible armyworm intrusions across the entire golf course. A sod producer uses a drone equipped with ground-penetrating radar, GPR, to measure root mass to determine which field or area of field is ready for harvest. All areas of turfgrass having sufficient root mass to harvest are mapped by variety using GPS coordinates. A ready-to-harvest map is created using GIS information and is matched by variety to the customer's order request. The day of harvest, with certain environmental parameters, such as soil moisture, temperature, and other factors set by the sod producer being satisfied, the harvest map is sent to a fully autonomous GPS harvester, which uses the information to cut, stack, and load the sod for the customer's order. A sports turf manager uses a mobile sensor unit to identify areas of soil compaction on several sports fields. The sensor unit uses 3 sensors to determine penetration resistance, soil moisture, and turfgrass stress along each field. All the data will be geo-referenced using GPS and GIS-generated individual spatial maps for each measured characteristic, creating layers of information. Once the layers of data are reviewed, Any area meeting the threshold of soil compaction needing aeration to correct the problem is mapped. The information detailing the coordinates is linked to a GPS core aerifier equipped with auto steer, a GPS guidance system which steers the unit across the sports fields. Using the GIS maps, the aerator is engaged to aerify all areas of each sports field needing aerification with centimeter accuracy. A lawn care technician uses a golf cart equipped with ground penetration radar calibrated to detect grubs within the root zone. The entire lawn is driven so that data can be collected and mapped. Across the lawn, having a threshold of a predetermined number of grubs per square foot are mapped with GPS accuracy. GIS mapping is used to indicate areas of the lawn that will benefit from treatment. This information is linked to a ride-on applicator, also equipped with GPS technology, and auto steer for treatment the same day. Will the next era of cutting-edge turfgrass equipment and technology as described above come to fruition? Well, it's important to remember what Chase Straw, PhD, Texas A&M said. I see new technology being used in precision agriculture, PA, and it's just a matter of time before it trickles down to precision turfgrass management, PTM. In fact, if you do a quick internet search for the type of technologies being tested and used in agriculture today, you will see that the scenarios above are within reach of all the cultural practices performed by the turfgrass industry. Another university researcher, David McCall, PhD, Virginia Tech, had this to say: the turfgrass industry is in its infancy of developing this new technology as compared to mainstream agriculture. However, turfgrass research has been moving so fast in the last 8 to 10 years that if you don't get the research published in 1 or 2 years, it could be outdated. So the short answer to that question is yes. One should remember that this new technology has been used in precision agriculture for 10 to 20 plus years. So precision turfgrass management research is able to ride the coattails, research, in most cases of precision agriculture, which partially explains why research is moving so fast in turfgrass. As in PA, innovations being developed today for turfgrass application are being applied across all operations, and many of these innovations will conserve inputs by only allowing them to be delivered to specific areas, SSMUs, where they are needed. This will improve input efficiency and minimize any potential negative environmental aspects. In part 1 of this article, specific areas, SSMUs, site-specific management units, were identified as areas with similar soil, topography, microclimate, and plant response. Inputs refers to fertilizers, pesticides, water, energy, and labor. The future horizon for equipment and technology, GPS and GIS. As you no doubt noticed, GPS, Global Positioning Systems technology, was mentioned in every scenario above. It's a location and tracking system that has the potential to be used with every cultural practice turfgrass managers perform: irrigation, applications of fertilizer and pesticide, cultivation, mowing, and harvesting. This technology will become ever more common with each passing year as it becomes available on most all new equipment going forward. It will be imperative for turfgrass managers to understand, operate, and utilize this feature, especially since it will have a direct and immediate impact on their operations to save time, money, and labor. It's the technology that tracks sensors identifying SSMU coordinates and directs GPS sprayers and spreaders to their targets while making applications. It provides steering coordinates to autonomous equipment while taking into account elevation, field boundaries, irrigation systems, nearby roads, buildings, and much more. You may notice that GNSS tracking is used by some equipment. GNSS is a term that refers to the International Multi-Constellation Satellite System, meaning this equipment's tracking system has access to more than just the GPS satellites. GNSS typically includes GPS, US, GLONASS, Russia, BIDO, China, Galileo, European, and many other constellation systems. GIS, Geographic Information System, is a computer-based tool that creates visual map representations of GPS data and performs spatial analysis in order to make informed decisions. It has been used for years in precision agriculture, comparing variables like soil type, wind direction, rainfall amount, slope, aspect, topography, and elevation to assist with crop management, site suitability, drainage planning, and much more. Researchers that use this technology say it's easy to see that the real power of GIS lies in its ability to quickly analyze multiple data layers or variables and create maps to illustrate the nature, degree, and implications of spatial differences to site managers so that budget priorities can be adjusted accordingly. The use of GPS and GIS technologies working together to assist precision turfgrass management is still in its inception. Researchers are learning how to best use the large amounts of spatial data to track and map turf response to soil moisture, fertility, soil compaction, weed pressure, insects and disease outbreaks, and inputs such as irrigation, fertilizers, and pesticides to make better informed, efficient decisions in the future. In addition to mapping, GPS, GIS technology could be instrumental in tracking and documenting all work and materials used, such as information related to gallons or pounds applied, square footage treated, time in the field, etc. This information can be stored separately in layers and used to track all inventories, labor, equipment maintenance, and service, and all other overhead costs, which could be applied to a computer model to monitor a budget or establish fees for service and materials. Sensors. The initial challenge limiting PTM has been the development of appropriate mobile sensor platforms for mapping both key soil and plant attributes. University and industry researchers see the future of turfgrass equipment being developed to work autonomously using sensor data collected by either stationary or mobile, aerial and ground, sensors to provide most, if not all, operations of turfgrass cultural practices. Ground penetrating radar. The principles involved with GPR are similar to seismology, except GPR methods implement electromagnetic energy rather than acoustic energy. GPR units are normally mounted to platforms that resemble push mowers, but tow-behind models are also available. Images produced by GPR equipment are called ground-penetrating radargrams and require time and experience to read with accuracy since the images look like screen distortion. Up to now, due to limited computational resources, we could only calculate radiation patterns of actual antennas up to a certain distance from the source. This is a subject of future research which will provide important information on the character of the recorded waves and will advance our understanding. Dr. David McCall said, ground penetrating radar allows researchers to look below the surface of the soil to look at water movement, root development, and even the depth of soil and the different layers of subsoil in many cases. It's understandable that GPR technology is also gaining popularity in identifying irrigation and drain lines under golf greens and sports fields, said Dr. Chase Straw. He added, it's actually being used now to spot broken irrigation pipe or clogged drain lines. There's also been some testing using the ground-penetrating radar to correlate surface hardness to the data collected by the Clegg hammer. If this becomes possible, GPR would make this measurement much easier and faster. However, the Clegg hammer would be less expensive. Interestingly, GPR has been used to detect the size of potatoes underground using a drone flyover, so researchers may in the future find a way to use this radar to detect the root mass of turfgrass. This could be a useful tool to help sod producers decide when to harvest their sod. In the future, there is no doubt that other uses for GPR technology will lead to some very interesting possibilities. Electromagnetic induction. EMI is a piece of equipment that operates as a toe-behind sled and resembles ground-penetrating radar, but it measures soil electrical conductivity, EC, or salinity. When used with a GPS system, it can generate salinity maps. Basically, this equipment uses electrical pulses directed downward and is highly correlated to clay content and organic matter. Dr. Straw said with GPS and GIS, it's possible to create a map indicating clay content and organic matter. However, more research is needed for it to benefit turfgrass managers because currently it measures soils down to about 20 inches. This may be useful to understanding drainage, but if the depth could be altered to capture only the depth of the turfgrass root zone, it could be very useful in making fertility decisions and the water holding capability of the soil. Thermal imaging, also known as infrared thermal imaging, IRTI. All objects emit infrared energy, known as a heat signature. Dr. McCall put it this way: a thermal imaging camera looks at the reflectance of wavelengths in the thermal range to detect heat transfer or hot spots. The most obvious reason to use this type of camera is to help map soil moisture levels. However, hot spots can be caused by things other than drought. It can also be used to determine if a plant or a series of plants, as with turfgrass, are transpiring properly. Using that information, researchers try to determine what's causing the plant to react in that manner. Early stages of pathogen development, such as brown patch and tall fescue, have been found to do the same. A graduate student working with Dr. McCall discovered that it was possible to see thermal patterns within tall fescue turfgrass that was being attacked by the brown patch pathogen several days before any visible symptoms became apparent to the eye. LIDAR, light detection and ranging. LIDAR uses eye-safe laser beams to see the world in 3D, providing machines and computers an accurate representation of the surveyed environment. Dr. McCall added, LIDAR allows researchers to look at certain surface characteristics, such as topography, to help determine if pests are developing in low-lying areas or higher elevations of turfgrass. Some cameras with motion sensors and LiDAR are being used to develop 3D models to identify and monitor the formation of lips at the interface of the infield and outfield on baseball and softball fields. If this technique could be perfected, it would allow the sports turf manager the ability to monitor and schedule corrective action before this maintenance practice became a problem. Multispectral and hyperspectral imagery. The sensors capturing these images are key to producing vegetation indices, VI, which are important measurements in plant analytics today and one of precision agriculture's biggest tools in remote sensing to understand plant health in real time. VIs are single numerical values minus 1.0 to 1.0 that are computed from multi-band images, photos, that can be used to quantify vegetation health. Images are typically taken by sensors from satellites, mobile ground units, or drones. Algorithms analyze the images and assess various aspects of plant, turfgrass, growth, vigor, biomass, green covering percentage, leaf area index, and chlorophyll content. Chlorophyll content can indicate early stages of drought stress. The higher the vegetation index number assigned to a plant aspect, presumably the higher plant vigor or health present. The normalized difference vegetation index, NDVI, is arguably the most common and well-known vegetation index. Toro Precision Sense 6000. The Toro company created a toe-behind mobile unit combining 5 sensors to capture a variety of measurements as it passes over turfgrass. The PS6000 collects data such as soil moisture, volumetric water content, VWC, salinity, compaction, turf vigor, normalized difference vegetation index, NDVI, and topography. Data is stored in an onboard computer during the collection process and relayed to Toro for creation of GIS-referenced map images. Turf managers can then receive two types of reports. One, precision irrigation audit, and or two, precision irrigation management zones. The PS 6000 was primarily designed to collect soil conditions on well-maintained lawns in parks, golf courses, sports fields, and commercial grounds. It's equipped with a foam marker to aid navigation by making the center line of each pass, with each pass being 10 to 15 feet apart. The optimum speed for collecting soil data is 3.1 kilometers per hour, 1.9 miles per hour. Drones. Also known as unmanned aerial vehicles, UAV, drones will have an ever-increasing role in the future of the turfgrass industry. Not only are drones used today to capture great real-time photographs and videos of ground conditions, but researchers are increasingly exploring the use of drones to carry a vast array of sensors to analyze a host of turfgrass conditions and making localized applications using drone sprayers in the future. Dr. Chase Straw stated, "More research is being done with drone sensors to learn how to better correlate the information collected to understand turfgrass real-time conditions and response to stress. The reason so much research is going in that direction is because drone data is so much easier and faster to collect." The same can be said for making drone applications of pesticides. Dr. Straw said, "Why drive to the far side of a golf course to make a few spot applications when a drone sprayer could be programmed to do it so much faster?" It should be noted that drone research for turfgrass use is still in the very early stages of development. Precision agriculture, on the other hand, has used drones for years and has the experience of correlating remote sensor information gathered not only by drones but also by satellites to document soil, pest, and environmental conditions to better understand and observe plant response to those conditions. The type and sophistication of sensors being used in agricultural research is growing, with potentially endless information being collected. Below are some of the sensors that drones currently use in agriculture that are also being used in turfgrass research. Phenotyping, spatial analysis, and vegetation indices are all being used to interpret the aerial data being collected per specific surveys. The area data is compared to on-ground tests and observations, ground truthing, to make sure the researchers understand the results so they can recalibrate their instruments to give even more accurate correlations of the results in the future. Current turfgrass research applications use drones to identify, monitor, and study the following: crop yield, growth, biomass, canopy density, nutrient status, water stress, disease incidence, weed infestation, chemical and nutrient applications, turf inventory management, species classification, invasive grasses and vegetation, especially in remote areas. At Virginia Tech, several researchers, including Dr. David McCall and Dr. Sean Eskew, along with Daiwan Ku, graduate research assistants, are working on ways to use drone technology to improve precision turfgrass management. One area of study receiving a great deal of attention is the use of spray drones. Here's what Dr. Eskew had to say. Spray drones are available from a number of manufacturers, ranging from smaller, consumer-level drones that carry 2.6 to 5.3 gallons to larger commercial types that carry 40 gallons or more. The biggest problem that limits further adoption of spray drone technology is regulatory uncertainty. He cites problems with no EPA pesticide registration for drone use, no formal position by EPA on spray drone registration, even though some states indicate that aerial application does extend to spray drones, and the increased regulatory burden associated with licensing through the Federal Aviation Administration. He also mentioned the following. Some research studies have shown successful weed control with spray drones, but the range of available equipment and possible application parameters could lead to inconsistent results. He then referenced the issues of drift caused by the drone's propellers, low pump capacities, and smaller spray tips that were subject to massive losses of spray deposition due to droplet vaporization and off-target drift, especially when drones are operated at heights greater than 6 feet. Dr. Askew said, "Our research suggests that successful drone spray deposition requires enough pump capacity to operate drift reduction spray tips, such as induction nozzles. Utilize nozzles evenly spaced along a boom similar to conventional ground equipment and be operated as close to the vegetation target as the spray drone will allow." It's clear to see the issues with government regulations, along with additional research regarding pump capacities, nozzle design and placement, as well as possible chemical formulations and drift control agents, will all need more answers before drones conduct aerial spraying. When drone spraying does become commonplace, it most likely will begin with sod producers first, followed by golf. This will definitely be one area to watch moving into the future. For all resources associated with this article, check out our show notes. Don't miss an episode. Subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can also visit us at theturfzone.com.
You've been listening to The Turf Zone. For more episodes of The Turf Zone, visit theturfzone.com and subscribe on Apple Podcasts, Stitcher, or your favorite podcast app.